All right, so let's do more integration by parts examples. Here's an example that's somewhat similar to the example we had at the end of class on Monday. We integrated x times sine of x first, and then we did x times natural log of x. Let's try x times inverse tangent of x. And yes, you can write that as x times arctangent of x as well. The inverse tangent and arctangent functions are the same thing. They are just different notations for the same function. Okay. Remember that with integration by parts, you want to write your integrand, the function being integrated, as the product of two functions that you call u and v prime. The trick is deciding what u and v prime should be. And the most important bit of advice is that v prime should be something relatively easy to integrate so that I can find v. Ideally, it's nice when u prime is something simpler than u is, but that's not absolutely necessary. It's tempting whenever you have an x or an x squared or an x cubed to always let that be the u. But that's actually a problem in the situation, because if that's the case, then arctangent would be v prime, and it's not clear what v should be. Integrating arctangent sounds difficult if you think about it. You know the derivative of arctangent is 1 over 1 plus x squared, but antiderivative of arctangent is not so clear. In fact, that'll be the next example I do. You actually have to use integration by parts for that as well, even though it seems to be just one function. So you don't want to let v prime be arctangent. You want it to let it be x in this example. And so that means u is the other thing. U is the arctangent. Most important bit of advice, again, is v prime should be something easy to integrate, and arctangent is not so easy to integrate. Once you've set up u and v prime, you find u prime and v, find u prime by differentiation, find v by integration. Do you need a plus c? No. Just put the plus c at the very end. That's all you need to do. The formula, which again I recommend writing down every time you use it. Get to a point where you can write it down without looking. You'll need that for the gateway anyway. Is that it's u times v minus the integral of v times u prime with respect to x. These are all functions of x. Okay. And I forgot to start this. Like I forgot last time. I got to get that play going or else it's going to freeze on me. So far, so good. Now just plug everything in. U times v is this upper left to lower right product. 1/2 x squared arctangent of x. What's v times u prime? Multiply the two things in the bottom there. So certainly that part's nice. Is this integral easier to do? Doesn't actually necessarily look like it is, and I purposely picked this one to be a little trickier. Integrating arctangent by itself is actually a little easier once you see the trick. Integrating this one, it's probably not clear what to do. You might think maybe a substitution works. But to tell you the truth, it's better to do something else first. To divide the fractions. Divide polynomials in this case. I'll bring the 1/2 down in front. But whenever you've got a rational function like this, where the degree of the top, 2, that's the highest power of x, is the same as the degree of the bottom, also 2, you actually want to divide those polynomials using long division. Yikes, that doesn't sound so nice. Well, here it's not so bad. Put the polynomial on top, the x squared. I'll bring the 1/2 out in front, so I Won't bother with the 1/2. Whatever's up top, in this case x squared, put it inside the long division symbol. Whatever's on the bottom, put it outside. And it's best to put it highest power to lowest power. So instead of writing 1 plus x squared, I'll write x squared plus 1. Not that you have to, it's just typically a little easier to think about. Now I want to do long division. Maybe you were never taught long division when you were 4th, 5th, 6th grade, because maybe your teacher said, well, you don't need long division. Let's just use a calculator. Yeah, you don't need long division for long division of numbers, at least if you only have calculators, but it is good to do long division of polynomials sometimes. And here's how you do it. Ask yourself, what do I need to multiply the highest power here, x squared by, to get the highest power there? It's almost too easy. What do I need to multiply x squared by to get x squared? 1. Do it. Put the 1 up there. Then actually multiply that thing, in this case 1, times this and put the answer down below the x squared. 1 times x squared is x squared, plus 1 times 1 is plus 1. So again, I'll say it again. Look at the highest power of x here and ask what you need to multiply it by to get the highest power of x there. Now, if that were an x cubed instead of an x squared, you'd have to multiply x squared by x to get x cubed, and you'd put an x up there instead. Then take whatever you put up there and multiply times this and put the answer down there. Then subtract. With long division, you subtract. X squared minus x squared is 0. 0, you don't see a 0 there, but it's implicit. 0 minus 1 is -1. 0 minus -1 here, this is a -1. Once you get something of a lower power than this, which this is a constant, definitely a lower power than this, you can stop. That is the remainder from the division, and the 1 up there is the quotient. In other words, I can say x squared over 1 plus x squared is 1 for the quotient, and with a remainder of -1. What does that mean? Think about it with numbers. This is just a side calculation. If I take 11 divided by 4, I'd say the quotient is 2 and the remainder is 3, right? 4 goes evenly into 11 2 times with a remainder of 3. But what does that mean? One thing it means is that 11 equals 2 times 4 plus 3. Another thing it means, if I divide everything by 4 and cancels those 4s, it also means the fraction 11/4 equals 2 plus 3/4. 2 and 3/4 as a mixed number. That's what I want to, that's the thing, the numerical analogy that I want to use with this function now. Go back up here. Again, don't forget to bring the 1/2 out in front. This function, x squared over 1 plus x squared, is the quotient, analogous to the 2 here. Our quotient is 1. Plus another fraction, which is the remainder, 3, over divided by the thing I was dividing by 4. For the polynomials, the remainder is -1, and the thing I was dividing by was x squared plus 1. The quotient is 1. The remainder is -1. I can rewrite the function like that. A little confusing, okay? But that works, and you can check it works too by actually subtracting here. I can bring that -1 down to the minus, make a minus sign right there. If I actually subtract 1 minus 1 over 1 plus x squared by getting a common denominator of 1 over 1 plus x squared, and then simplify by combining those fractions, the 1 and the -1 cancel. That's a 2 there, by the way. The 1 and the -1 cancel, and you're left with x squared over 1 plus x squared. The same thing I wanted. Back up there again, I brought the 1/2 in front. So this subtraction confirms that this is the same as the original function. And now both of those are relatively easy to do. I'm going to get 1/2 x squared arctangent of x, don't forget that. Minus 1/2, first of all, times the integral of 1. I'll go ahead and write it out. You don't have to write it out like I'm doing, but it doesn't hurt. And then the two minus signs make a plus sign, 1/2 times the integral of 1/1 plus x squared. And yeah, those integrals are both easy to do. I hope you can see. Here I'm just integrating 1, giving me x. Here I'm integrating 1/1 plus x squared. That's a memorized integral. That's arctangent. That should be correct if I have not made any mistake. I could check it by differentiation, and notice if I did, I'd have to use the product rule. Remember I said, anytime you check an integration by parts, you've got to use the product rule. Let's do it two ways with Mathematica to save time. The original function was x times arctangent of x. You have to type that into Mathematica like that, with a capital A and a capital T. Look this over, you see a negative x over 2, that's the same as negative 1/2 x. You see an arctangent of x over 2, that's the same as this one. And you see 1/2 x squared arctangent of x. Wait a minute. Mathematica would not pass the gateway. It didn't put a plus c. Well, the authors of Mathematica know you should put a plus c, but they're just leaving that to you. Okay. So whenever you check this with an indefinite integral in Mathematica, it does not put the plus c, but you should.
You also solve that problem by using substitution for the second integral after you do the integration by parts.
You mean this one?
Like, yeah, like,
You could try a substitution like w equals 1 plus x squared, for example.
yeah, and then solve for.
Yeah, I think it's probably not going to work so easy. It's better to do the long division. You can also check this by differentiation, though I will tell you that if I do that like this, the capital D does the differentiation, it may not be simplified. Let's see what it looks like. Yeah, it doesn't look simplified. You can fix that. You can do like / simplify at the end, and there it simplifies. The / is just another way of doing an operation in Mathematica. Put the function you want to apply, in this case, the simplify function at the end. I don't have to do it that way. I could do it at the beginning as well, like this. And then there's no slashes. Okay, so that was a pretty tricky problem, in part because we had to use integration by parts, and also in part, no pun intended, because you had to do the long division. You have to do the long division anytime you've got a rational function where the degree of the top is at least as big as the degree of the bottom, greater than or equal to the degree of the bottom. If the degree of the top is smaller, like 1 or 0, then you don't have to do long division, like we didn't have to with that one. Let's do actually an easier integration by parts example. Just integrating arctangent. It's ultimately easier, though it seems trickier at first. And again, I could call that inverse tangent as well. By the way, when you write an inverse tangent like that, it does not mean tangent to the -1 power. It's not 1 over the tangent. That's inconsistent notation with a lot of other things in math where you have a -1 power. But I'm just telling you, it's not. If you meant to raise tangent of x to the -1 power, you'd either put parentheses around the tangent of x and then put a -1 power, or you'd write it as cotangent of x. Cotangent is the official name of the reciprocal of the tangent function, 1 over the tangent function. Wait a minute, how could I possibly use integration by parts here? Doesn't the integrand have to be the product of two functions? This one doesn't look like it is until you do a little trick, until you put a 1 in there. Of course, anything times 1 is the anything. Yeah, arctangent of x is the same as 1 times arctangent of x. And 1 can be thought of as a constant function. Just like the previous example, we need to let the arctangent of x be the u. Because if we let it be the v prime, then we'd be trying to solve the exact same problem we're trying to solve, to find v, right? If you know v prime and you're trying to find v, if I let v prime be arctangent of x, to find v, I'm doing the same exact problem I'm already doing. So v prime has to be the other function, 1. Differentiate this one to get 1 over 1 plus x squared. Integrate this one to get just an x. Remember, it's a good idea to write down the integration by parts formula every time you use it. uv minus the integral of v times u prime. I mentioned this on Monday. If you've taken calculus before and you've done integration by parts before from some other textbook, you may have called this dv, effectively dv equals dx. And you may have called this du and put an extra dx at the end. That's a somewhat more traditional way of doing it, but I think this way is a little conceptually simpler. To not bother with the dv's and the du's and the dx's. That gets a little bit more confusing. Though you do want to do that with substitution, as we've seen. So again, use it now. U times v is the product of those two things. X times arctangent of x minus the integral of the product of these two things, which becomes x over 1 plus x squared. That's a rational function right there. But don't do long division. This time, the top has a degree smaller than the degree of the bottom. Degree means the highest power. The degree of this one is 1. That's the highest power of x. The degree of the bottom is 2. You don't have to use partial fractions for that kind of thing. So what do? Whoever asked the question a few minutes ago about the other one, who was that? Yeah, do substitution. Yes, sometimes you have to combine the rules, substitution and integration by parts. For this one, I could let w be 1 plus x squared. That means dw is 2x dx. I see an x dx up there. I better divide both sides of this by 2 to get 1/2 dw is x dx. I will replace the x dx with 1/2 dw. Don't forget to include the first term. Don't forget to include the 1/2. We're almost done. Now integrate that second integral. You'll get 1/2 times the natural log. Interesting. Why would we get a natural log? That's kind of weird. It is weird, but it is true also. Of the absolute value, here you do need absolute value signs. The w here could be positive or negative. Well, in the end, we actually don't need absolute value signs because w is 1 plus x squared. And as long as x is a real number, that's always positive. So I do not need the absolute value signs in the end. It doesn't hurt to put them there. So as a default, you might want to always put them there. But I actually don't need absolute value signs right there, since 1 plus x squared is always positive. For all real numbers x. If x is an imaginary number, or more generally a complex number, it's possible 1 plus x squared could be a negative real number. It's possible. But we're not dealing with imaginary numbers right now. We actually will talk about them a little bit in 2 months, maybe, somewhere around there, when we do infinite series. I mean, it's weird, but it must work. Again, to check it, you use the product rule right there. Okay, maybe for the sake of believing in and not just trusting Mathematica, let's go ahead and do it this time. Let's check it by differentiation. If I differentiate this, evidently it must simplify to that. That's not at all obvious, but let's try it. So apply the derivative operator, d dx. That's what I mean when I draw this kind of arrow on a d dx. I mean, take the derivative. I need the product rule. First times second function. The derivative of the first, x, is just 1 times the second function plus the first function, x, times the derivative of the second. The derivative of arctangent is 1 over 1 plus x squared. Minus now the derivative of this, which I need the chain rule for, and maybe you can start to see already how this is going to turn out. The derivative of natural log of something is 1 over the something, but then the something is not just an x, it's a 1 plus x squared, so I need to multiply times the derivative of that something. Derivative of the inside function of this composition. 1 plus x squared is inside function, natural log is the outside function. C differentiates to 0. The 2's divide out there and there. And then this is x over 1 plus x squared minus really x over 1 plus x squared. And those then cancel like magic. And you're left with arctangent of x. It checks. Cancellation had to happen if we're going to get something simpler at the end. Sometimes you've got to use integration by parts more than once in the same problem, is what I mean. Let's find the integral of x squared times, let's make it negative e to the negative 2x. This kind of integral, I'm just telling you right now, when you use integration by parts for this, which you should, you're actually going to have to use it 2 times. The first time you use it, you will get another integral that's a little simpler than this, but not quite simple enough to do without parts again. If it were x cubed, you'd have to use it 3 times. If it were x to the 4th, you'd have to use it 4 times. Yikes. Well, we can also use technology, but getting practice with this, again, makes math more real, right? If you're just relying on the technology, math feels like a purely technological thing. And you really, I think, don't do as well as you would unless you actually do the calculations yourself. Making things concrete is a good idea. It also, for example, in some later classes, could help you believe what the professor is doing if you've gotten enough practice with this. You're going to have to use it twice. When you have an x squared there, or maybe a constant times x squared, times e to a power, or maybe sine of something, or maybe cosine of something. Those are examples where you need to use it twice. You want v prime to be something easy to integrate to find v, and you want u to be something, well, easy to differentiate, and maybe so that u prime is simpler. And here it is a good idea to let u equal x squared so that u prime is 2x, and v prime be the other factor, e to the negative 2x. Although I did make this a little trickier by making this power negative 2x instead of x. To find v here, I need to integrate this, but it's a little tricky. To be extra careful, you'd want to do a substitution to find v. W equals negative 2x, say. But once you've got enough practice with this stuff, in situations like this, you can just guess the answer. And there's the correct guess. Why? Think about it. If you check this by differentiation, you'd have the negative 1/2 still there, times e to the negative 2x, times by the chain rule, another factor of negative 2, right? The derivative of negative 2x is negative 2. And the negative 2 and the negative 1/2 would cancel to give you positive 1, which is what's in front of the e to the negative 2x, though I didn't write it. So we get u times v minus the integral of v times u prime with respect to x. U times v is the product of those two things, negative 1/2 x squared e to the negative 2x, minus the integral of the product of these two things. Product of those two things, the 2's cancel, but there's a negative sign still that does not cancel. However, that negative sign could cancel with this negative sign if I bring it out in front. I'll do it in 2 steps. I multiply these two, I cancel the 2's. The negative sign stays there. I still have an x and an e to the negative 2x. But now these two negative signs can cancel. So you can write this. But that is, again, another integration by parts problem. It's simpler than the original one because I've got a lower power of x. But to be extra careful, I need to do integration by parts again. Double check my work, make sure I don't make mistakes, check for sign errors, check for cancellation errors. I think everything's right. For here, let u equal x and v prime be e to the negative 2x. Then u prime will be 1 and v will be negative 1/2 e to the negative 2x. Don't forget your first term, negative 1/2 x squared e to the negative 2x. Plus, okay, use parentheses to be careful. U times v is the product of those two things. There's going to be a negative sign, negative 1/2 x e to the negative 2x. Minus the integration by parts formula involves a minus sign, the integral of the product of those two things. See where I'm pointing? V and u prime. There's another negative sign. I could again do it in 2 steps, but let me go ahead and cancel with this other negative sign to get a plus sign. I also need to bring the 1/2 in front. Or I can at least, I don't have to, but. And now that integral is an integral we've already done a couple times in finding the v's. So what's the final answer? Negative 1/2 x squared e to the negative 2x minus 1/2 x e to the negative 2x. Integrate this with the 1/2 in front. I'm going to get a minus 1/4 e to the negative 2x. Now add the plus c at the end. If we check this by differentiation, we need the product rule again. In fact, we need it twice. I guess that's because we had to do integration by parts twice. Let's go ahead and do that. Let's check it by differentiation. Take the derivative with respect to x. Use the product rule, first function, second function in each case. Be really careful about negative signs here. This is tricky. If I differentiate the first function here, negative 1/2 x, I'll get negative x times the second function plus the first function, negative 1/2 x squared, times the derivative of the second which by the chain rule gives me e to the negative 2x times negative 2. Oh boy, so easy to make a mistake here. Got to be really careful. That's the derivative of just this first part so far. Now I'm on to the second part. I can either subtract the derivative of this thing, or I could think of this as plus this first function with a negative sign times the second function. Either way is okay as long as you're careful. The derivative of negative 1/2 x is negative 1/2. So there is the derivative of the first function times the second function, minus or plus the first function, which is negative 1/2 x, times the derivative of the second function. Once again, that's e to the negative 2x times negative 2. On to the derivative of this. I'm going to get an extra factor of negative 2, canceling with that negative sign, and then 2 times 1/4 is 1/2. I'll get a plus 1/2 e to the negative 2x. Plus 0 when you differentiate c. I've been writing the plus 0, you don't have to. What's supposed to happen here? I guess a bunch of stuff must cancel because I'm supposed to get x squared e to the negative 2x at the end. Okay, we better be careful. Well, okay, this cancels with this for sure. And yeah, let's see. This ends up equaling plus x e to the negative 2x. And that cancels with this one. So the final answer is this, whatever that simplifies to. And the negative signs cancel, it simplifies, the 2's cancel to x squared e to the negative 2x. After cancellation, that's the final derivative, and therefore it matches this, and therefore we are correct. Okay, I'm showing my work in kind of a sloppy way for the sake of time. You would want to probably write in equals and keep simplifying. It checks, right? Tracking with me? Not zoning out? All right. Yet another problem. You could do infinitely many integration by parts problems. Not that I will require that. Integrate, how about, let's make it a little tricky. E to the 2x times cosine of 3x. This one's pretty tricky. It's a product of two functions, one of which should be u and one of which should be v prime. Which should I choose? Should I choose u to be e to the 2x and v prime to be cosine of 3x? Or the other way around, v prime being e to the 2x and u being cosine of 3x? The answer is it actually doesn't matter in this problem. Either way is okay. You might wonder how that's going to happen, but I do claim either way is okay. Okay, we'll go ahead and do it that way. But the other way is okay as well. And they're about equivalent in difficulty, actually. Once we've got u and v prime, we need to find u prime and v. Differentiate u to find u prime. You're going to get a negative 3 sine 3x, right? Chain rule again. Integrate e to the 2x. Now I'm going to get a positive 1/2 e to the 2x. uv minus the integral of v times u prime with respect to x. Everything's a function of x. u times v is the product of these two things. 1/2 e to the 2x cos 3x minus the integral of v times u prime, the product of those two things. I'm going to go a little faster here. The negative sign will cancel with this negative sign to give me a plus sign. And 3 times 1/2 is 3/2. I'm going to factor the 3/2 out. And I'm left with the product of e to the 2x and sine 3x inside the integral. But wait a minute. That integral doesn't look any simpler, does it? It's basically the same thing, except with a sine instead of a cosine. Seems like we're spinning our wheels. Well, don't let it deter you. Do integration by parts again for this integral. Be consistent with how you define u and v in the first integral, u and v prime in the first integral. Be consistent. Since I let u be the trig function and v prime be the exponential function, do the same thing over here. If you do the opposite thing, I think you can't solve the problem. Do the same. Let u be the trig function, sine 3x, and v prime be the exponential function, e to the 2x. Be consistent, and it'll work out. It's not clear how, but it, like magic, will.
Is there a situation where, you could end up going sort of infinite of integration by parts, and you get something integration by parts, you get something.
Yep. In fact, it feels like it could be an infinite loop right here. Because, doing this resulted in something similar with the sine. You might think that if I do it again, I'll get something similar with the cosine again. And that does happen, but you still can solve the problem, it turns out. I've got to find u prime and v again. There they are. Now use the same formula again. Don't forget about your first term, though. That gets carried along for the ride here. Don't forget the 3 halves out in front and use parentheses. U times v is 1/2 e to the 2x sine 3x minus the integral of v times u prime. Now the minus sign does not cancel, but I can bring in 3 halves out in front. Yeah, it seems like we're spinning our wheels here. Seems like we haven't made any progress. But you actually have, because what you can do now is you can algebraically solve for the integral you want to know. It's just a number. Oh, well, okay. If you think of, it's a function, okay? I want to solve for this integral as an unknown function. I want to solve a linear equation in the integral. Here's what I mean. First, distribute the 3 halves through the parentheses. To get, for the first term, there are 3/4 e to the 2x sine 3x. And for the next one, a minus 9/4 integral of e to the 2x cos 3x. We're saying that this is one way to write this original integral. That original integral, if integration by parts is true, which it is, will equal all this. You might wonder, well, how does the plus c come into play? Well, don't worry about it. We'll just lop that on at the end. I need to solve for the unknown integral. Add 9/4 times the integral to both sides, so that the integral on the right side cancels. If I do it to the right side, I got to do it to the left side. These cancel, including the 9/4. Over here, the integral that I want to know plus 9/4 times that same integral is 13/4 times that same integral, because 1 is 4/4. Now to solve the problem, just divide both, well, multiply both sides by 4/13. Should I put a plus c here yet? I mean, you can. Maybe I'll call it C1, because then the C at the final end will be 4/13 times C1. It's not a big deal. Question? What did I forget? Thank you. Yeah, multiply both sides by 4/13 now. The integral of e to the 2x cosine of 3x, 4/13 times 1/2. Do a side calculation if you need to. 4/13 times 1/2. The 2 cancels with the 4 to give you 2/13. Four 4/13 times this fraction, 3/4. The 4's completely cancel, leaving you with 3/13. And then I'm going to call 3/14 times C1, I'll just call it C. I'm fine if you just put the plus C on at the end and you don't bother with the C1. But don't forget the plus C at the end. By the way, just a second. You may wonder, are these problems going to show up in the gateway? No, nothing this difficult shows up in the gateway. Okay, the gateway is about more basic problems, still with integration by parts sometimes, but easier. Question? I'm adding this integral plus that integral, and this integral did not have a times 1 there to begin with, but here I'm trying to put a times 1. Yeah, 1 is 4/4, and so 4/4 plus 9/4 is 13/4. It's very possible I can make mistakes, so please be looking for mistakes. Here's how you'd have to type it in Mathematica with a capital E to represent the number E. Capital C in the cosine function, square brackets for the input of the cosine function. Not square brackets around the 2x there because that's a power. Parentheses instead. There we go, looks good. Again, Mathematica fails the gateway because it forgets the plus C. No, it's programmed to not bother. The author of Mathematica, Stephen Wolfram, is assuming you know to add the plus C. By the way, I once was in an elevator with Stephen Wolfram, and after he'd just given a talk, so I get to talk to him a little bit. But he's actually a very famous person. I think I was hoping to do more about why integration by parts and substitution works. Save that for Friday after the mini exam.